Good afternoon, this is Father Eckstedt, and this is installment number 3, lecture 3 of our Calc 1 course here at DeSales. And we're having an online class today because class was canceled due to the weather. So as to not fall behind on the schedule, we'll do this online version. So in this particular section, we're talking about functions and models in chapter 1, and more specifically in section 3, we're talking about getting new functions from old functions. And to me, that's a little misleading. So I think a better topic or way of labeling this section is transformations of functions. So we're going to talk about transforming functions to get new functions. So the old function will be what we start with, and the new function will be what we make it into or transform it into, and you'll see what I mean very soon. I've copied this diagram directly from page 37 in the textbook, and in the very center in black is this function labeled f of x. And we've chosen a rather arbitrary point in the diagram. All right. And we've talked about what happens if we take this function and move it up, down, left, or right. By applying certain transformations, by adding or subtracting c, either from the x or the y, we can get graphs of related functions. Having this skill will allow us to sketch graphs of many functions quickly by hand. It'll also enable us to write equations for graphs given when we're asked, well, what's the transformation that was made to this given graph to result in this answer or this resulting graph. So we're considering here in this diagram, again, I've copied it from page 37. You might want to have a good look at that diagram. What happens when we add c or subtract c? So as you can see, if you add c, all the y's are now exactly c units more than they were before. So this point on the black function is picked up exactly c units, right? And the whole function is just c units more than it was before. By way of contrast, think about if you subtracted c. Now all the y's would exactly be c less than they were before. So this particular value on the function would now be c less, and we'd move everything down exactly c units, and the result would be this green graph down below. Now, one of the things that the books don't often talk about is the fact that this is the same thing as saying y plus c equals f of x. And it might be more helpful to think of it this way when we think of the left-right movements that we're going to look at in just a second here. Consider this red one up top. That another way of considering this one would be y minus c equals f of x. And for the red one, you might say, well, to go back to the original f of x, I'd have to take c units away from the red one to get back to the black one. Or if we're talking about the green one, and we're looking at the graph y plus c equals f of x, I'd have to add c back to every point on the green one to get myself back to f of x. And I think that is maybe helpful when we start looking at moving left and right. And notice now that the plus c and the minus c, in this case the minus c, is trapped inside the parentheses. It's paired with x. So now the operation is a horizontal movement. It happens to be take this point and move to the right exactly c units. And think about that. I'd have to take c units away from x, every x, to get myself back to where the black one is. It may seem counterintuitive that this blue one moves to the right when we subtract c. But if you stop and think about it, we would have to take c away from every x to move ourselves back to the black one. And maybe that's the way to think about it. So one last one here to look at would be this yellow one. And think about this. If we are exactly c units back, we would have to add c on, right? Notice that the c is with the x. We'd have to add c on to take ourselves back to where we have f of x. So let's take and put some values into a c, and let's take a look at a function that we're familiar with, namely f of x equals x squared. Consider this parabola y equals x squared. Very familiar function, I think. It's a quadratic function. Sometimes I call this the unit parabola. And we could set up a table and put values in for x and solve for y and get a series of points. And so over here on the left with the graph, I have a point that's plotted at negative 2, 4. So negative 2, 4 is part of the sketch up here, right? So let's just put that on there, label it on there. And there is a point at 2, 4. And a point back at negative 1, 1. And a point at 1, 1. And of course a point at the origin. Now let's think about taking this original function, the one here that's drawn in black, y equals x squared, and let's consider some vertical movements, some vertical shifts, we say. Consider that if we go up 2 units, and let me just change my color to red here, y equals x squared plus 2. All the y's are now 2 more than they were before. This would be the same as saying y minus 2 equals x squared. To get us back to x squared, we'd have to subtract 2 away from every y on the red curve to bring us back to the black original. So that's one vertical shift we can do. That's moving up. Let's consider what happens when we move down. Well, if we move down, consider what I've done here at the left. Y equals, isn't that x squared minus 4? Haven't we gone down 2 with the green one? Down 4, excuse me. And another way of expressing it might be y plus 4 equals x squared, where we'd have to bring every y up 4 units to restore it to where the original was. Now consider the horizontal shifts. Horizontal shifts are moving right and left, like the horizon. Shifts, not shifts. Shifts. There we go. F, right? So let's consider this one here in blue. And wouldn't this be y equals, now we've got to put it with the x, so wouldn't that be x minus 6 quantity squared? Every x, you'd have to subtract 6 from the blue one to restore it back to where the black one is. This is over to the right exactly 6 units. And again, this might seem counterintuitive unless you start comparing it with this one and this one, those horizontal shifts where you thought about restoring it to the original one. That's what I like to do here, that it's over 6, so you'd have to take 6 away to get it back to where it was originally to make it x squared. And the final one, the yellow one, over on the far left there, the way I've drawn that one, we'll change this to yellow when we're done here like magic. So 4 would be, well, y equals, and it has to be with the x, and we'd say plus 5, and that would be, take it to the left 5 units, right? So if we were to add 5 to everyone on the yellow curve, it would restore us back to the original black one. Let me change that black into yellow. There it is, like magic. Now it is yellow to correspond to the yellow graph. On the top of page 37 in the textbook, you will see this little chart or table that summarizes all the changes that you can do to move things around, move a function around vertically, that is up down, or left right, horizontally. So vertically we're talking about movements up or down, right? Whereas horizontal, we're talking about movements to the left or to the right. So consider the table. Consider and read this table carefully. If there's just a c added onto the end, and it's not with the x, notice that we go c units up. Every y is c units more than it was before. If we subtract the c from the end, we go c units down. If the c, the value that we're going to add or subtract, is paired with the x, as it is in these last two, and if it's a minus c, then we're going to move not to the left, as you might think because of the negative sign, but we're going to move c units to the right. And finally, the last one will be c units to the left. So these are the two that seem to mess people up at times. Thinking clearly about when you subtract c from the x, you're actually moving to the right. And if you add c to the x, you're actually moving to the left. Towards the bottom of page 37, there's a second table that summarizes what happens when the function is stretched or reflected. And let's talk about stretching first of all. Once again, in this particular diagram, the original function is here in the middle, drawn in black. If I take and multiply the function by a number greater than 1, all right? If I double it or triple it or whatever, every value of the function now is twice as much, or perhaps with this red one as it's drawn, based on the scale, I'm thinking it's about 3 times as much. So if this was at the point 1, 1, this is at the point 1, 3. Looking at another point here, if this is at 2, then if this one's 3 times more, this is at 6. So it's pulled or stretched. If this one, if it went from 1 to 3 and this is back at 2 and it is tripled, then this would be at 2 times 3 or 6, right? So let's just make some quick notations for these points. So once again, if the point at 1, 1 is stretched by a factor of 3, every y is now 3 times as much as it was before. If we apply that transformation to the point at 2, 3, and every y is 3 times as much as it was before, this would go up now to 9. If this point here on the black one is said to be at 3, 2, then every y would be 3 times as much if the value out front were 3. So it would go from 2 to 3 times more, which would be 6. So now we've taken and stretched, we've allowed c equals 3. Now, I've just imposed that on this, right? It doesn't necessarily, it looks like it's something less than 3 when I look at it, but that gives you an idea about how those things would be applied. Now I've removed all my notations with the red graph that we said was tripled, and consider the one underneath it where, for the sake of illustration, let's say it's 1/2. That is, the C for this green one is, yeah, I'm on the green. The C this time has to be between 0 and 1. That is, this value out in front here, if we consider that the C, let's consider it as 1/2. And so the way that they've done it here in the book is really sort of a disservice. This should not be written this way. This should be written, this is C times f of x, but now the C is between 0 and 1. So it works or corresponds to this one. Anyway, I'm not the author of the book, so I just make that, I think, a little clarification there. So anyway, consider now that what was at 1, 1, now if the y's are half as much, we'd be having a point at 1, 1/2. Or if we had a point at 2, 3, the 3 would be cut in half and we'd have 2, 3/2. Or rather than a point at 3, 2, we'd now cut that y in half and have a point at 3, 1. So this would be considered a shrink when the c's are between 0 and 1, some fraction. And when the c's are greater than 1, we say it would be a stretch. So the red and the green represent the stretch and the shrink vertically. Now, and that's the green one. Now, we go into horizontal stretches and shrinks, and I don't believe they are illustrated in this picture. We can work at some of those with my next graph, but let's take a look at these reflections. And let's say every y is now opposite of what it was before. So every y is now exactly opposite of what it was before. So with this yellow one, if we look at this opposite graph down here, not a point at 1, 1, but a point at 1, negative 1. So this corner point would be at 1, negative 1. The y is now opposite. Or this point that was at 2, 3, now this opposite graph, where the y's are opposite, would have a point at 2, negative 3. And the yellow graph would have a point not at 3, 2, but at 3, negative 2. Exactly the opposite of what it was before. Here it is originally, right, the black one. And the yellow one is what we call a transformation. It's a reflection across the x-axis. And when you reflect across the x-axis, you have this negative sign in front. So that's this one here towards the bottom. When you have the negative sign out in front, when you make all the y's opposite of what they were before, it'll reflect about the x-axis. And finally, if the negative sign is put in front of the x, and that's what we have in this final case here, where the x's are now negative, you would have a point back here at negative 1, 1. The x's are now opposite. And you'd have a point at negative 2, 3. That corresponds to this point at 2, 3. And you have a point at negative 3, 2 back here. So the blue one is a reflection across the y-axis. You might think about if you folded the paper up on the y-axis, if you folded this page or this projection up on the y-axis, and the black ink over here on the right was wet, if this was wet ink, it would take and leave a track over here when we folded it up, and it would be that reflection exactly across the y-axis. So that does our reflections and our vertical stretches and shrinks. So let's take a look one more time now at that graph of y equals x squared. Consider a vertical stretch on our parabola y equals x squared. If I take now and put a number greater, I don't know what happened there, a number greater than 1, if I stretch x squared, if I put a factor in front of the function x squared, I get a new set of y's, we'll call them the red y's, and if I put 0 in and square it, I still get 0, and 0 times 2 is still 0. But now, when I put 1 in or negative 1 in, I get 2 out. And when I put in 2 or negative 2, I now get 8 out. In other words, everything's doubled. And so now this original graph is now stretched by a factor of 2, we say. It's taking off quicker. So this point up here is at 2, 8, right? This point, original point at 2, 4 is now doubled. The y's are now twice as much. Or what was at 1, 1 is now over here. This is at the point 1, 2. And I won't make it any messier by adding more things to it. I haven't been talking all this time. I've been drawing on this green one, and I meant to pause the video and I didn't. But but you get the idea. I put a negative 1/2 out front. Now I'm doing a reflection with the negative sign. I'm making all the y's opposite, and then I'm doing what's called a vertical shrink by putting a number in front that's between 0 and 1. So this number is between 0 and 1, this c, right, this constant. And this time I chose a 1/2. And so if you put a 1/2 in front of the function, you get this set of new y's. I'll call them the green y's. And notice that if you put in, for instance, 2, you square it, of course, and get 4, but times a negative 1/2 gives you a negative 2. Or back here, when you put in negative 2 and you square it, you get 4, but 4 times a negative 1/2 takes you to negative 2. And I added some additional points here that aren't in the table. For instance, if you put 3 in and you squared 3, you'd get 9, but 9 times a negative 1/2 is negative 9/2, or negative 4.5. And similarly over here, I put a point in what's going on at negative 3, and what's going on at negative 3 is negative 3 squared is 9, and 9 times a negative 1/2 is negative 9/2, which is negative 4.5. So you get an idea now about doing two things: a reflection with the negative sign and what we'd call a vertical shrink by putting a number in less than 1, in this case a 1/2. Let's take this one and consider what would happen if we put something in with the x. Let me pause here for a second and draw it up. So this time, notice with the x, I've put a factor in front of it, in this case 2. And notice when I do that, the quantity now 2x squared is the same thing or equivalent to 4x squared. And now if I put in my values for x, I get a new set of y's. We'll call them the red y's. And notice that when I plot these points, what happens is I get this very tall, or this parabola that's taking off very quickly. And notice that this is a horizontal shrink. That when this value is greater than 1, when the c value is greater than 1, you'll get a horizontal shrink. And notice that, now horizontally, like what was the space between negative 1 and 1, now has become this little bit right in here, or up here when it used to be, a full 4 units across between negative 2 and positive 2. Now it's shrunk up, right? And it will just take off very quickly when we put a number in front of that. It will tighten up this parabola. It'll be horizontally much tighter than it was before. We call it a horizontal shrink. Now I've added the green graph, and notice that the number, the c value that I put in front of the x here, is now a fractional number, a number between 0 and 1. And when I take and square this quantity, where I have the c with the x, I get 1/4 x squared. And that will produce a new set of outputs, a new set of y's, right? I'll call them the green y's up here. And when I put 0 in, of course, I get 0 out. But when I put 1 and negative 1 in, I get 1/4 out. Or when I put a 2 in for x, I get 2 squared is 4, but 1/4 of 4 is 1, right? So I get a new set, and I plotted those points over here, like here's the point at 4, 1, and back here we have the point at negative 4, 1. And I'm sorry my hand isn't steadier on this graphing pad, but it gives you an idea about how now when the number is between 0 and 1, you'll have what's called a horizontal stretch. The parabola will get very flat. So that's something to be said now about horizontal stretches and shrinks. Now let's look at what is coming up here to finish off this chapter, and that's what we call combinations of functions. We're finishing off this section by talking about combinations of functions, and they can be taking two functions and adding them together, as you have here, or perhaps subtracting them from each other. And this is two ways of saying the same thing. F plus g of x is like saying f of x plus g of x, or f minus g of x is the way we read it, and it's the same thing as saying f of x minus g of x. Now this will be more typical, what's over here on the right with both of these. And the same over here with multiplication and division. Yes, this is fg of x, which will render as f of x times g of x, or f over g of x, more typically rendered as f of x over g of x. These are all called composition function. They're composed of two or more. They're either add, subtract, multiply, divide. They could be roots and powers of the functions, although they get a little more complicated when we introduce those two operations, roots and powers. This last group is what we call composite functions. Let's get my pen activated here. Composite functions. And let's change colors back to, well, let's make it red. And let's consider the function f of u. And let's say f of u says, all right, what I do is I take the square root. I'm the square root function. Whatever is in for u, I take the square root of it. I'm the square root function. Let's consider another function. Let's call it the g function. And the g function is, I take a number, square it, and add 1. So square and add 1. Now, if we come up with what's called a composite function, we would simply say, well, let's make this f not of u, but f of another function. So let's put in g of x for u. If we do that, g of x is x squared plus 1. And finally, if we apply the f rule or function to this quantity, remember the f rule is the square root rule, so we're going to take the square root of this x squared plus 1. Notice that's quite different than if we were asked to do g of f of x, because f of x is, well, the square root of e of x. Remember, the f function is take the square root of whatever is in this case it's an x, and then the g function says take whatever you got, in this case the square root of x, and square it and add 1. This would result in x plus 1, something quite different than what we got when we took f of g of x. The order matters, the order of application. Let's do that one more time. And this time let's do it with three functions. Let's say we have f of x is the squaring function. Let's say g of x is, well, let's say that it's taking and adding a number like 4 to any value. And let's say we have the h function, which is take and find the cubed root of whatever you've got. So let's take a couple of compositions like f of g. Well, take my g of x out and put in its place what g of x is, and isn't that x plus 4? Recall that f is the squaring function, right? So that means take whatever you've got and square it. Now that's a binomial squared, so be careful. That's the same thing as x squared plus 8x plus 16. Remember, that's like saying x plus 4 times itself. And if you did FOIL on that, right, wouldn't you get first times first is x squared, outsides and insides together would give you the 8x, and then 4 times 4 gives you the 16. That's going to be quite different than g of f of x, because g of f of x would mean take g, the g rule, and apply it to what f of x is, and f of x is the same thing as x squared, and then the g rule says take whatever you've got and add 4 to it. What we have is x squared. The g rule says whatever you've got, take and add 4 to it. So now we've got x squared within the parentheses, so we get x squared plus 4, something quite different. And of course we can get very creative with these, so we can put them in different orders and say, how about h of f of g of x? Well, we already did f of g of x over here, right? And we said it was this. So we can say, well, let's take that, right? And let's apply the h rule to it, x squared plus 8x plus 16. And the h rule says take the cubed root of whatever you've got. So it's the cubed root of x squared plus 8x plus 16. Consider if I asked you for f of h of g of x. Go to the most inside, replace the g of x. So we're going to find f of h of g of x is simply x plus 4. The h rule, which we'll apply next, the next most inside, the h rule says take the cubed root of whatever you've got, so that's f of the cubed root of x plus 4. And finally, the f rule says square whatever you have. So the answer is going to be the cubed root of the quantity x plus 4, quantity squared, which is the same thing as saying x plus 4, the quantity raised to the 2/3 power. So we're getting a little lengthy here, so I'll let you go. But we'll see you on Wednesday. And take a good look at the examples in Section 3. And I think you'll find it pretty straightforward. We'll do some looking at in class at some of the problems from Sections 2 and 3. That's all for now.